Welcome back to Mastering Algorithm series. In previous video, we learned what an algorithm is. But here is an interesting question. Suppose two developers solve the same problem. Both programs give the correct answer. So which solution is better? The answer is not based on who wrote fewer lines of code. It is based on how efficiently the algorithm works. Today we will understand time complexity and big O notation, the language developers use to compare algorithms. Don't worry if you have heard that big O is difficult. By end of this video, you will understand it with simple examples. Imagine two developers write code to find a student's roll number. Both return the correct answer. The first program finishes in 1 second. The second one takes 10 seconds. Which one would you use? Obviously, the first one. Now imagine the database grows from 100 students to 1 million students. The difference becomes much larger. One algorithm may still finish quickly while the other becomes painfully slow. Time complexity helps us predict this behavior before our application reaches production. Here is something beginners often misunderstand. Time complexity is not the actual execution time. The same program can run faster on a gaming PC and slower on an old laptop. Even closing background applications can change the timing. Execution time depends on processor speed, RAM, operating system, compiler optimizations. Because hardware changes, measuring only seconds is unreliable. Instead, we study how the algorithm grows as the input size grows. Imagine you are searching for a name in a notebook. If there are only 10 names, finding someone is easy. If there are 1000 names, you will spend more time. With 1 million names, the same approach becomes much slower. The important question isn't how many seconds, it's how does the work increase when the input increases. That's exactly what Big O measures. Let's say we want to find the number 91. We start from the beginning. Compare with 15, not found. Compare with 23, not found. Then 8, 42, 67. Finally, we reach 91. In the worst case, we may have to check every element. If the array has 10 numbers, we may check 10 times. If it has 1000 numbers, we may check 1000 times. If it has 1 million numbers, we may check 1 million times. This growth is called ON, or linear time. In previous example, we checked every element one by one. But what if our data is already sorted? Can we do something smarter? The answer is yes. And that's exactly what binary search does. Instead of starting from the beginning, binary search starts with the middle element. Let's see how it works. Suppose we want to find the number 70 in this sorted array. Our first step is to look at the middle element. The middle is 50. Now we ask a simple question. Is 70 equal to 50? No. Then we ask another question. Is 70 greater than 50? Yes. That means something very important. Since the array is sorted, every number to the left of 50 is smaller than 50. So there is absolutely no point searching there. We can safely ignore the entire left half. Just like that, we have eliminated half of the array with a simple comparison. Now we are left with 60, 70, 80, 90. Again, we choose the middle. This time the middle is 70. Is it our target? Yes. We are done. Notice what happened. We found the number after checking only two elements. We never looked at 10, 20, 30 or 40. We didn't need to. The sorted order helped us eliminate unnecessary work. Now let's compare these two algorithms side by side. Don't focus on the formulas. Instead, focus on how quickly the amount of work grows. Suppose our application has only 10 records. If we use linear search, we might need to check all 10 records. With binary search, we need only about 4 comparisons. At this point, both algorithms seem fast enough. You probably won't even notice much difference. Now imagine our database grows to 100 records. Linear search may perform 100 comparisons. Binary search still needs only about 7 comparisons. That's already more than 14 times fewer operations. Now let's think even bigger. Imagine an e-commerce website with 1000 products. Linear search could perform 1000 comparisons. Binary search needs only around 10. Notice something interesting here. The data became 10 times larger, but binary search barely increased its work. Now, let's go to a real world scale. Imagine a company has 1 million customer records. If we use linear search, the computer might check 1 million entries in the worst case. Binary search, only about 20 comparisons. Think about that. One algorithm needs 1 million steps, the other needs only 20. That is an enormous difference. This is exactly why companies care about algorithms. When your application is small, almost any solution works. But when millions of users start using your application, choosing the right algorithm becomes critical. Sometimes you don't need a faster computer, you simply need a smarter algorithm. Imagine you enter a library with 1 million books. Method 1, start at the first shelf and check every single book until you find the one you want. That's like a linear search. Now imagine the books are arranged alphabetically. You immediately go to the correct section, then narrow your search again. Then again, within a few steps, you have found the book. That's binary search. The library didn't become smaller. You simply used a much smarter strategy. This is why interviewers don't just ask, can you solve this problem? They also ask, can you solve it more efficiently? A candidate who knows both linear search and binary search may produce the same answer, but the candidate who chooses binary search demonstrates stronger algorithmic thinking. These are the most common complexities you will encounter. O1 means constant time. No matter how large the input becomes, the work stays the same. O log n grows slowly. On means the work grows linearly. O n log n is common in efficient sorting algorithms like merge sort and quick sort. O n square often appears in simple nested loops such as bubble sort. Finally, O to the power n grows extremely fast and becomes impractical for large inputs. Our goal as developers is to choose the most efficient algorithm that still solves the problem correctly. Suppose you are attending a conference with 5,000 people. You need to find your friend. Option 1, walk around asking everyone. Option 2, use the alphabetical registration list. Both methods work, but one is dramatically faster. This is exactly what algorithms are about. Choosing the smarter approach instead of simply working harder. During interviews, after you solve a problem, you will almost always hear this question: what is the time complexity of your solution? Interviewers ask this because they want to know whether you can analyze your own code. Writing correct code is only half the job. Understanding its efficiency is equally important. Now that you know what big O notation represents, but how do we calculate it from Java code? If you see a loop, nested loops, or recursion, how do you determine the complexity? That's exactly what we will learn in the next episode. We will calculate the time complexity of real Java code step by step. Thank you for watching. We'll see you in next video.